In this video, we define non-uniform Poisson point processes, and also we give an example about telegraph signal. So if the points that happen in time, so this is a Poisson point process. So let's say this is the first point, is the first T1, this is T2, T3, etc. And then you have a Poisson process here is 1, then you go 2, etc. So if the distribution of this function is not uniform density, if lambda is changing with time, then we need to update, because for the case that we had uniform distribution, we had P of I, T, comma, S equal K was equal to T minus S times lambda to the power of K divided by K factorial, and this e to the power minus T minus S times lambda for K equals 0, etc. Now, if lambda is varying with time, then instead of this parameter, instead of this guy, we need to use integral. So we substitute T minus S lambda by integral from T to S. So here, if we assume that S is bigger, so we should have put S minus T. S minus T. Okay, so S minus T. So if you do that, we get this expression. So this is a distribution of a non-uniform density Poisson point. For instance, the traffic rate, when you use your internet more, lambda goes up. And when all people are asleep, lambda or traffic rate in city will become much smaller. How many people are using internet? A telegraph signal is a Poisson point process. We remember that for a Poisson point process, we defined, we start with time t and say here is 1, and then at the second point becomes 2, etc. But alternatively, instead of defining a Poisson point process with the number which goes increasing, and it's hard to keep mind, you could define these point process using telegraph signal, which is a binary random process. So in the first interval we put 1, and in the second interval we put -1. So a telegraph signal is a binary signal which starts at 1, and at the discrete points it toggles to -1, and so on. So we define x of t, or telegraph signal, to be equal to 1 if we have even number of points in the interval between 0 to time t. Otherwise, if this is odd, we put -1. So this random process, the toggling points, they give you the points of the points in time. So at the first point you get 1, then you get -1, then you get 1, and so these edges of these poles, they give you the discrete point in time. So there is a one-to-one relationship between x of t, and let's say this is t1, this is time t2, that's time t3, t4, etc. So the sequence of tn, which is the point process, this is a sequence of random variable, is defined in a one-to-one relationship with x of t. Now, we can calculate what is probability of x of t being equal to 1. Obviously, x of t is 1 if n of t is even. So this is equal to probability that n of t is even. Obviously, we have probability of PDF, probability mass function of n of t. We know that p of n of t equal k is equal to e to the power of minus lambda t, and then lambda t to the power of k, k factorial, and k being equal to 0 to etc. So we can use this one. So we don't want n of t be equal to exactly k, but we want it to be even. So this becomes equal to summation over all k equal to even. So which is equal to, k is equal to twice L, and L becomes equal to 0 to plus infinity of probability that n of t is equal to twice L, and this is becoming a sum of L equals 0 to plus infinity e to the power minus lambda t divided by 2L factorial, and then lambda t to the power of 2L. And then you could simplify this sum and get the answer for this probability. So this is equal to probability that x of t is equal to, or 0 is even, 2, etc. And if you do that, you get this summation, and then you can simplify it. So this is becoming e to the power minus lambda t cosine hyperbolic of t. Obviously, you can calculate probability of x of t equal minus 1, which is equal to 1 minus probability of x of t equal 1, because there is no other alternative, and this is going to become equal to e to the power minus lambda t sine hyperbolic of lambda t. Now, using that, you can calculate expected value of x of t, or average of this one, using that, because this is equal to the value that x of t can take on. Two values can take on, 1 or minus 1. So I get 1 times probability of x of t equal 1. Remember that this is the value, and this is the probability that x takes this one. So these two guys are equal. Okay, and then plus minus 1, probability that x of t is equal to minus 1. And this guy is same as this one. So you get e to the power of minus lambda t cosine hyperbolic of lambda t, and then minus e to the power minus lambda t sine hyperbolic of lambda t. And then you could simplify this one and get your result. So it becomes e to the power of this one. So if you plot this function, you see that it starts from 1, because if t is equal to 0, e to the power of 0 is 1, and then exponentially this will reduce. So the slope of this one is equal to 1 over 2 lambda. So if the lambda is large, this will decrease faster. So for telegraph signal, we have calculated mean of x of t for telegraph signal, which is mu xt. So the first order moment. We want to calculate the second order moment. So we want to calculate this one. Obviously, this is equal to mean of this x at time t1, x of t1, and then mean of x at time t2, x at time t2. So these random variable, or these two random variables, are binary. So they take values of plus minus 1. So this is equal to the value that this guy can take, this value that this guy can take. So it's going to be 1 times probability that x of t1 is equal to 1, and then probability that x of t2 is equal to 1. X of t2 is equal to 1, and then plus all other 3 alternatives, because we have 4 cases. So for simplicity, we assume that t1 is bigger than t2, so this is time, and this is, let's say, t1, and this is t2. and we know that for telegraph signals, these two guys are not independent. However, their increment, the number of points in this time interval, is independent of the number of points in any other interval. Okay, so I write here the number of points in, let's say, time interval t2 and t1 is independent with any other interval. So if you have another interval here, the number of points here and the number of points here are independent. So we want to use this one in order to calculate this probability. So we write it as a conditional probability. So we say probability of the second be 1, given that xt2 1 times probability of that. So this is one event, this is another event, so you can write the conditional probability. This one we have already calculated in previous slide, and this one, if at time t2, so this is time t2 and this is time t1, at this one xt2 is 1, so it's like at this time is like you are at time 0. So this one we have already calculated, except that we have to substitute t1 minus t2 in the previous expression. So you get e to the power of so this one will become e to the power of minus lambda t2 cosine hyperbolic of t2, and the first one you get e to the power of minus lambda t cosine hyperbolic of lambda t. Remember that lambda t is time difference. So this initial condition at time t2 means that the number of points at time t2 is event, but how many points will happen will give you the same expression. So we multiply these two. Now if you multiply these two, you will be able to simplify. So this is equal to this will give you e to the power of minus lambda t1 and so on. Similarly, you can calculate all these other terms. Please do this as an exercise. Please go over step by step. If you need, you can also look at the expression of cosine hyperbolic. Remember that cosine hyperbolic of, let's say, a is equal to e to the power of a minus e to plus e to the power of minus a divided by 2, and sine hyperbolic of a is equal to e to the power of a minus e to the power of minus a divided by 2. So you could calculate probability of xt1 and xt2 to take different binary values of plus minus 1. And now that we have all these ones, so we have four different cases, then you can calculate expected value of xt1, xt2, because I want to calculate probability of these two guys taking plus minus 1. So in that case, this guy, if you consider 4 cases, 4 number and so on, so that means that you multiply this one by 1, multiply this by minus 1, this one by 1, minus 1, multiply this by plus 1, and this one by minus 1, and then add 4 terms together, simplify them, you get this one. So you see that if you plot, if you take 2 samples at time, let's say t2 and let's say t1, and this time difference is t, then the autocorrelation function of rxx is only a function of the time difference here, and for the time difference t is reducing like that. So if I plot it versus only t, not t1 or t2, it is reducing exponentially. So that means that the points xt1, xt2, if time t1 and t2 are away from each other, they become uncorrelated. And if they are very close together, they are highly correlated. Obviously, this binary signal toggles with higher probability if you have more intervals, because more points could potentially be there.